Good morning, Math 30-1. Today we are going to be doing our last lesson of Trig 2, which is solving trigonometric equations using identities. Now, when we're solving these trig equations, you need to make sure that you are going to be using some substitutions using trig identities. So that whole right column on your formula sheet, we're going to be now using those to help us solve. Now, usually this involves ensuring that the equation is written in terms of one trig function. So that means usually we try to write it all in sine, all in cosine, and sometimes all in tangent. So we have our first example. If you guys printed out the notes, because this is not in your workbooks, today we're going to be solving a couple examples. The first one, solve the equation in this domain from 0 to 2 pi. So again, we want to make sure that when we're solving from 0 to 2 pi, that our answers are in radians. Notice how this first equation looks. Okay, I'm going to write out what a couple things you need to make sure that you do. Number one, always replace a double angle. So if you look at this first example, we have a double angle in here. So we always want to get rid of that. Second, look for any Pythagorean identities. So those ones are usually the ones that say you have something squared. So if I look at this second answer, we have something like 1 minus cos squared. That would be where a Pythagorean identity would be. And number 3, we always want to replace our quotient or reciprocal identities. So those are things like tangent, cotangent, cosecant, and secant. We like to get rid of those. So now that we kind of have a few strategies of what we start to replace, if I look at this first example, we have cos of 2x plus 1 minus cos of x is equal to 0. Now I can't solve with that double angle in there, so I'm going to take out that double angle and I'm going to replace it. Now the tricky part about this one is that on our formula sheets we actually have 3 versions, and we can pick any of the 3 versions, but remember our goal here is try to write this all in terms of sine or cosine. So if I pick the first one of cos squared minus sine squared, it's not going to get rid of the cos. This is my clue. The fact that I have a cos x and it's linear, it's not squared, I can't replace that with anything. So I want to write this first equation cos. So what I'm going to replace this one with is the one that just has cos in it. So 2 cos squared x minus 1. I still have this plus 1, and then I still have a minus cos of x. Don't forget to make it equal to 0. Now you can see that here our 1's are going to cancel. So we're really just left with 2 cos squared x minus cos x is equal to 0. From here, I'm going to look to factor. So I have a greatest common factor of cos x, so I'm going to take it out. I'm left with 2 cos of x minus 1 equals 0. And now we have something that we did all the way back in our first lesson in this chapter, where we solve. So we take this cos x, make it equal to 0. We take this bracket and make it equal to 0. Now here, we know that cos of x is equal to 0 in my domain from 0 to 2 pi, at pi over 2 and 3 pi over 2. So that's the first one. The second one, we isolate our cos x, so we move our 1 and divide by 2, and we know that cos equals 1/2 at pi over 3 and 5 pi over 3. And that's using our CRA steps. And we have 4 solutions for this equation. I do want to check for non-permissible values. But in this case, we had no reciprocal and no quotient, so there are none. But you do want to check that when we are solving. And that is the first one. Okay, let's go ahead and try the second one. 1 minus cos squared x equals 3 sine x minus 2. Again, this is the linear one. We cannot get rid of sine x. We can't replace it with anything. So we're going to use our cos squared x plus sine squared x equals 1 Pythagorean identity to help us solve this one. So we are going to replace cos squared x. I want to get it as sine. So I know that sine squared x is actually equal to 1 minus cos squared x using this identity. So this is simply sine squared x. I'm going to bring this stuff over to the other side. So I'm going to get minus 3 sine x plus 2 equals 0. Again, this is something that we factored before. If you need to let your sine x equals a in order to factor it, you can factor that and then plug back in your sine x's. I'm just going to factor this with my sine in there. I'm going to get sine x minus 1 and sine x minus 2 is equal to 0. And so what happens here is I'm going to get sine x is equal to 1 and sine x is equal to 2. Now here, there's no solution. We know that sine cannot equal 2. The largest sine can be is positive 1, and the smallest it can be is negative 1. Now over on this side, we know that sine is equal to 1 pi over 2, and so this equation only has one solution. Now you guys can pause the video and you guys can give these two a try. And I will put the solutions up for you. Okay, so for here we have a double angle again, so we're going to replace it. We're going to replace it with 2 sine x cos x minus cos x equal to 0. We can factor out our cos x. We're left with 2 sine x minus 1. And now we have cos x equals 0 and sine x equals positive 1/2. We know that this one happens at pi over 2 and 3 pi over 2. And this one happens at pi over 6 and 5 pi over 6. Over here for the second one you guys would have tried, here's our Pythagorean identity, which is cos squared x. I'm going to bring over this 3, make it equal to 0, and of course we still have our 2 cos of x. From here, we're going to get, well, I'll rearrange it because it's a little bit easier to see how to factor it. We'll put our cos squareds first, plus 2 cos of x minus 3 is equal to 0. We're going to factor into cos x plus 3 and cos x minus 1 equals 0. We're going to get cos of x is equal to negative 3 and cos of x equals positive 1. Again, we know it can't be greater than 1 or negative 1, so this part has no solution. But cos x equals 1 at x is equal to 0. It could also be at 2 pi, but notice here in our domain, it's not equal to 2 pi. Be careful, always check your domain. So we only have one solution, x is equal to 0. Now, we're going to move on to example number 2 on the next page that has us solving with something like cotangent in it. So again, we do want to replace our reciprocal identities in our equation. So we have cos squared x equals cotangent x sine x. I'm going to replace this cotangent with what it's equal to, which is cos over sine. And you can notice right here, our sine x's cancel. Be careful. This question does say verify our answer. We know that sine x, because it's in the original equation, cannot equal to 0. So if we get a solution that means where sine x is equal to 0, have non-permissible values. From here, to continue solving, I'm just going to bring over my cos x and make it equal to 0, factor out a cos x, and state that cos of x is equal to 0 and cos x equals 1. Now cos equals 0 at 90 degrees and 270. Cos x equals 1 at 0, degrees or 360. Let's check if 360 is in our domain. It's not. And we have 3 solutions. Now, I do want to verify and check, well, where is sine x equal to 0? Well, sine x is equal to 0 at 0 degrees and 180 degrees. So I go back to my solutions, and this is a non-permissible value, and this only actually has 2 solutions, 90 and 270. Graphically, you can punch the left side into the calculator versus the right side, and you can verify your solution. So let's have a look at that right now. So I'm going to pull up my calculator. We're going to go into our y equals, and we're going to put in our cos squared. So remember to do that. You have to go cos x, close both brackets. Oh, sorry. Y equals bracket cos x, close both brackets so you're not squaring your angle, and make it squared. I'm going to do intersection, so I'm going to make the left side cos squared and the right side. I can't put in cotangent, so I'm going to put in 1 over tan of x, close both brackets, times sine x. I'm going to go to my window. I'm going to change my domain, or my x max and min, from 0 to 360, which is what my domain is. I'm going to change my scale to 30, and my max and min for my y values don't really matter. I'm just going to leave it at 0 to 10. I'm going to go to my mode and make sure that my mode is in degree mode. I'm going to press enter, and then I'm going to hit graph. So there's our first graph, and there's our second graph. So it looks like I should change my window a little bit so I can see those intersections a little bit clearer. And I'm just going to go and change my y max to maybe 4, just so I can see things a little bit better. And so you can see our points of intersection over here and over here. And so we can go second trace, intersect, and we can scroll over to that first intersection over here. Press enter, enter, enter. And we can see that we get an intersection of 90 degrees. I could do it again over on this side. Probably would have been better if my window went down to something like -2. Just so we can see that red graph a little bit better. And there you go. You can even, we set our scale at 30 degrees. You can even see 30, 60, 90, and then again over here at our 180. Notice right here, there is a non-permissible value because there's a hole in the graph. And that is how you can verify graphically. So if you'd like to, you guys can give this one a try. I'm not going to do it because this video is going to get pretty long if I keep going. But it is just something in degrees, so if you wanted to, you can try it using your calculator as well, and you're going to get a solution of 30 degrees and 150 degrees, 0 degrees, and 180 degrees for that one. Here, again, all we're going to do is replace our double angle, factor it out, and find a solution. What's new about this one is it says general solution. So I'll do this one really quickly. So here, we're going to replace our double angle. We're going to replace it with our 2 sine x, cos x, and then I'm going to bring this one to the other side. Now from here, I'm going to recognize that I have a greatest common factor of cos x, so I'm going to take that out. I'm left with 2 sine x minus root 2 equals 0. Again, I make cos x equals to 0. Happens a lot. And over here, we're going to get 2 sine x minus root 2 equals 0. Cos x equals 0 happens at our pi over 2 and our 3 pi over 2. But again, this domain was all real numbers, or general solution. So we're just going to say x is equal to pi over 2 plus pi n when n is an integer. Over here, we're going to make our sine x equal to root 2 over 2. We know that this happens at pi over 4 and 3 pi over 4. Now we're solving it in the domain 0 to 2 pi, and from there we're going to use these as our principal angles, or our principal solutions, and we say pi over 4 plus pi n when n is an integer, and we will also say 3 pi over 4 plus pi n when n is an integer. And we don't have to pull those together into one solution. We can just leave it as that. And those are our 3 solutions for this one. Now again, you have a you try question. It has a double angle. You have to decide what to replace it with. So remember that this one has a cos x, so you're going to want to choose the one that has just cos in it, so the 1 minus cos squared, or whatever you are, sorry, the 2 cos squared x minus 1. This one is going to have a general solution, just so you have it, at 2 pi n, 2 pi over 3 plus 2 pi n, and 4 pi over 3 plus 2 pi n, all when n is an integer. Okay, there's one last example that I'll go through with you, and then we're done for trigonometry. This is your last example. Here we're going to just bring everything to one side, and then we're going to look at the fact that this one needs to be replaced with 1 over sine x. So we're going to get 2 sine x minus 7 plus 3 cosecant x is equal to 0. When I go and replace this with 1 over sine x, I don't want it on the denominator. So just like we remember in 20-1, when we want to get rid of a denominator, it means I multiply every term by sine x, and by sine x. So we're allowed to do that as long as we multiply every single term in the equation by sine x. So what happens here is we get 2 sine squared x minus 7 sine x, and here my signs cancel, and I'm left with plus 3. Now this is something that can be factored by decomposition. So just to show that, we're going to get 2 sine squared x minus 6 sine x minus sine x plus 3. Factor by grouping. Take out my 2 sine x over here. I'm left with sine x minus 3. I'm going to take out a -1, and I'm going to be left with sine x minus 3. My new greatest common factor is sine x minus 3. And all the other stuff goes in its own bracket. And now I go and solve it just like we have been. We have sine of x is equal to 3, no solution. And sine x equals positive 1/2, which happens at pi over 6 and 5 pi over 6, which we can just say in general, pi over 6 plus pi n, 2 pi n, not pi n, when n is an integer, and 5 pi over 6 plus 2 pi n when n is an integer. I just want to double check that I said 2 pi n, yeah, on the last one. Sorry, so over here, this one should have been 2 pi n and 2 pi n. And that's it. That is today's lesson. So you guys can work on the worksheet that has been provided. The solutions are, the answers are there. There's no work through solutions, but I'm sure if you have any questions, your teachers will be more than happy to help you out.